Hi guys, in the last lecture what we covered was, we first of all saw what is a wound rotor induction motor. In there we saw that the rotor side is always connected in start no matter whatever is the stator connection. And then we saw there is a provision for adding external resistance in a wound rotor induction motor through the brushes into the slip rings. Okay, and the slip rings are insulated from the shaft by a mica insulation. Okay, the external resistance had two purposes, that the starting torque increased and starting current reduced. But the copper losses also increased due to the external resistance, and it could also be used for speed control. Okay, then we saw working of the induction motor, in which I told you whenever the stator flux will cut the rotor conductors, then the rotor will try to catch up with the stator flux to reduce the relative speed to 0. In such a case, rotor will rotate in the same direction as the stator field and the relative speed would be reduced. So we defined slip something like ns minus nr by ns. Okay, and we saw that the rotor frequency was sf. So the speed of rotor magnetic field with respect to rotor was 120 into sf by p, that is sns, and the total speed of the rotor field was sns plus rotor speed, which was sns plus ns 1 minus s, which is equal to ns. So we saw that the rotor and the stator field both rotate at a synchronous speed, so their relative speed was 0. This was one of the conditions that we referred to earlier also, that both fields in a machine should be stationary with respect to each other for production of a steady torque. Then we saw inverted induction motor. In inverted induction motor, we had the supply connected to rotor. So it produced a rotating magnetic field with respect to rotor. It rotated at a speed ns with respect to rotor. And when it cuts the stator conductor, then rotor starts rotating in the opposite direction to reduce the relative speed between the stator conductors and the rotor magnetic field. So rotor rotates at a speed ns 1 minus s, but in a direction opposite to the magnetic field. And when it rotates in a direction opposite to the magnetic field, the total speed of the field becomes s times ns with respect to stator. Okay, so here the stator frequency becomes s into f, where f is the rotor frequency. So in case of normal induction motor, rotor frequency is sf. In case of inverted induction motor, stator frequency is sf. So let us see a problem based on the speed of different magnetic field. So here it is saying a 3-phase 12-pole 50 Hz wound rotor induction motor is to be used as frequency changer. Okay, as I told you, a wound rotor induction motor provides electrical output across the slip rings, but the frequency at the slip rings is different from the stator frequency, hence it is used as a frequency changer. This induction motor is driven by adjustable speed DC motor. Okay, so DC motor is working as a prime mover and rotating the shaft of the motor, assuming field to be rotating clockwise. We need output frequency 100 Hz to 300 Hz. We need to find the speed range of DC motor. So rotor frequency must be 100 Hz to 300 Hz. Stator frequency is 50 Hz. So slip, we can say slip will be 2 or 6, 100 by 50 and 300 by 50, because rotor frequency is equal to slip times the stator frequency. If it is 2, it is greater than 1, so I will write ns plus nr by ns. Okay, greater than 1 means rotor and the stator magnetic field are rotating in the opposite direction. That is why when we are calculating the relative speed, we are adding both the speed. Okay, ns I can easily calculate. 120 into f is 50, number of poles are 12, so it is 500 rpm. So from here nr would be how much? 1000 minus 500, which is 500 rpm. Okay, so minimum speed of the rotor is 500 rpm, and that is anti-clockwise because it is rotating opposite to the magnetic field. If magnetic field is clockwise, it will be anti-clockwise. Next, let us take 6. 6 will be ns plus nr by ns. So nr will be 5 times ns, or we can say 2500 rpm. So the speed range of DC motor is 500 to 2500 rpm in a anti-clockwise direction. But see, I can even take the slip to be negative. The negative slip means that the rotor is rotating at a speed higher than the stator. What if I take the slip to be minus 2 and minus 6? See, the rotor frequency is SF, it can never be negative. So only the magnitude of slip matters, not the sign of the slip. Because even if you write FR is minus 100 Hertz, it does not make any sense. FR can only be 100 Hertz. Okay, frequency can never be negative. So minus 2 will be equal to ns minus nr by ns. So ns will be, nr will be 3 times ns, which is 1500 rpm, and here it will be minus 6 equal to ns minus nr by ns. Nr will be 7 times ns, that is 3500 rpm. Since I am doing ns minus nr here, I am assuming both the speeds in the same direction. So 1500 to 3500, but clockwise. So there can be two possibilities: 500 to 2500 in the anti-clockwise direction, or 1500 to 3500 in the clockwise direction. Okay. So there are two possibilities, that the rotor speed is 500 to 2500 rpm in anti-clockwise direction, or it is 1500 to 3500 rpm in clockwise direction. Okay, in both the cases, the rotor frequency will be 100 Hertz to 300 Hertz. So by this method, we can step up or step down the frequency using a induction machine. That is why induction machine can be used as a frequency changer. Okay. Now let us see what kind of EMFs and currents are induced in the rotor due to the stator winding. So first of all, let us talk about rotor EMF. EMF induced in any winding is 4.44 F N phi kW. So since we are talking about rotor, it will be E2 4.44 FR N phi kW2. kW2 means winding factor of winding 2 or the rotor winding. FR means rotor frequency. Now at standstill, standstill means NR is 0. Then slip will be 1. So rotor frequency will be SF, that is equal to F. Okay, when the motor is in standstill condition, slip is 1. So rotor frequency is same as the stator frequency. So EMF will be 4.44 F N phi kW2. Okay. Now when it is running, let us assume a slip S. So rotor frequency will be SF. So EMF will be, let us say E2 dash will be 4.44 SFN phi kW2. So it is equal to S times E2. So under running condition, the induced EMF is taken S times the EMF at standstill condition. Okay. So EMF becomes S time. Let us talk about what happens to rotor impedance. In rotor, we consider two components, R2 and X2. Now, again at standstill, slip will be 1. So Z2 will be R2 plus J X2. And when running, slip will be, let us say, S. So Z2 dash will be R2 plus J2 pi SF into L2, which is R2 plus JSX2. Okay. So reactance is multiplied by S because reactance is proportional to frequency. Okay. So Z2 dash magnitude will be under root R2 square plus SX2 square. Here the magnitude of Z2 would be under root R2 square plus X2 square. Okay. Now that EMF and impedance has changed, current will also change. So current in standstill condition, I2 would be E2 by under root R2 square plus X2 square. And under running condition, it will be S times E2 over under root R2 square plus SX2 square. Okay, now what to do is take S common from the numerator and denominator. It will be E2 by R2 by S whole square plus X2 square. Now why I am doing this is, see, EMF and reactance depend on frequency, and if they are multiplied by S, it indicates that their frequency is S times the stator frequency. But in case of transformer, what happened was both the frequencies on primary and secondary were same. Okay, that is why I was able to refer the secondary circuit to the primary and primary circuit to the secondary. But here frequencies are different, so I am not able to transfer the circuit. So that is why I am trying to make frequency same. How I am making the frequency same? By making the current in this manner. If I am writing the current like this current is same as I2 dash only. But here E2 is appearing as E2 and X2 is appearing as X2. There is no S terms in the frequency dependent term. E2 and X2 are frequency dependent, and since there is no term containing the slip, that means their frequency is assumed to be equal to stator frequency. Okay. And here the angle at which I2 will lag V2 will be tan inverse X2 divided by R2 by S, which is tan inverse Sx2 by R2. Okay, by this angle current will lag the voltage, that is the impedance angle. So now I can represent it in form of a circuit, a reactance and a variable resistance. Variable why? Because it depends on slip S. This will be R2 by S. This will be X2. Here EMF will be E2. Okay. So this will be my rotor circuit. Here the current will be I2. Now let us talk about the power. The power will be simply E2 I2 cos of theta 2. Okay, E2 is simply E2. I2 is E2 by under root R2 by S square plus X2 square cos theta 2. Cos theta 2 will be R by Z, that is R2 by S divided by under root R2 by S whole square plus X2 square. So it will be E2 square R2 by S divided by R2 by S whole square plus X2 square. This will be the power injected at the rotor. Now see, power in the rotor comes from the stator. So this power is transferred to rotor from the stator, and between the stator and the rotor there is air gap. So power is transferred from stator to rotor through the air gap. This is called as air gap power. It can also be written as I2 square R2 by S, because this term combined with this is I2 square into R2 by S. Okay. Now we know that copper loss in rotor will be how much? I2 square R2. So I can write this power as the total air gap power will be I2 square R2 plus I2 square R2 1 by S minus 1. Okay, because the formula was I2 square R2 by S, so I am adding and subtracting I2 square R2. This will be my copper loss. And see, the power injected at the rotor is air gap power. Some of it is lost as the copper loss, and rest of the power will be delivered at the shaft. So rest is mechanical power. Okay, it is also called as developed mechanical power. Okay, so here copper loss will be equal to I2 square R2, which is equal to S times air gap power, and mechanical power will be I2 square R2 1 minus S upon S, which is 1 minus S times Pg. So copper loss plus mechanical power loss will be totally equal to the air gap power. Now after the mechanical developed power is there, there will be some losses in the shaft. Okay, the shaft losses will be rotational losses. So shaft power will be mechanical power minus the rotational loss. This will be my shaft power. What about torque? To calculate the developed torque, will be developed power by omega. Now developed power is 1 minus S into Pg. Speed of the rotor is omega S into 1 minus S, which is equal to Pg by omega S. So this is the developed torque in a induction machine. Air gap power divided by the synchronous speed in radian per second. Okay. But what about the shaft torque? Shaft torque will be shaft power divided by omega. Shaft power is mechanical minus rotational loss divided by omega S into 1 minus S. So that is how we can calculate the shaft torque. Okay. So what are the various losses in case of a DC machine? First of all, input power will be coming from the three-phase AC supply. Then there will be some copper loss in the stator. Then core loss. Core loss means hysteresis plus eddy current. So these losses will be stator core loss. Then we will get the air gap power. So to get the air gap power, we subtract the stator losses from the input power. Then there will be some rotor copper loss, then rotor core loss, and here we will get the mechanical developed power, which is Pg into 1 minus S. And after subtracting the friction loss, that is the rotational loss, we will get the shaft power. So shaft power is nothing but mechanical power minus rotational loss. So it is very necessary that you remember this power flow diagram so as to calculate the efficiency. Efficiency will be shaft power by P input into 100. So you need to know from where to subtract what losses. For that you need to know the location of each and every loss. In what part what all losses are encountered. Out of this, stator copper loss and rotor copper loss depend on the load, and core losses are independent of the load. Friction and windage loss are also independent of the load. So let us summarize what we have learnt in this lecture. We first saw that induction motor can be used as a frequency changer. Then we saw what is the rotor EMF. So there we saw E2 dash is SE2, and we saw X2 dash is equal to S times X2. Then we found out the rotor current. We found out the rotor power, which is called as air gap power, which is E2 square by r2 by s whole square plus x2 square into r2 by s, or it can be written as I2 square into r2 by s. So remember, you have to consider a factor of 3 here when we are talking about 3 phase. If it is written as like 3 e phase square by r2 by s whole square plus x2 square. Here we were drawing the circuit per phase, that is why I haven't taken a factor of 3. But if you are calculating total power, you have to take a factor of 3. Then we saw mechanical power was equal to air gap power into 1 minus s. Copper losses was equal to s into air gap power. Shaft power was mechanical power minus rotational loss. Okay, so this is what we learnt in this lecture. In the next lecture, we'll solve some problems based on speed of different magnetic field and whatever we have covered up till now.